right, let's do this.
Okay.
Great. Good morning, good afternoon.
Oh, just wait. We're just admitting. There we go.
Good morning, good afternoon. On behalf of the Canadian Academy of Engineering, it is my pleasure to welcome you, the CAE Fellows, members of other academies and organizations, and students to this webinar on achieving net zero by 2050, challenges and opportunities of electrification and electric cars. This webinar at the National Engineering Month is dedicated to all engineers across the country in recognition of their work doing such a great job helping our country. My name is Soheil Asgarpour, PTAC president and president-elect for the Canadian Academy of Engineering. This webinar is the second webinar in the series dedicated to net zero emissions to discuss the common challenges Canadians face with meeting this target and how collaboration and innovation can get us closer to achieving it while maintaining Canada's economic prosperity. You can view the presentations and video of the first webinar on the Academy's website. To inform our students and members of other organizations who may not be familiar with our organization, the Academy is the national institution through which Canada's most distinguished and experienced engineers provide strategic advice on matters of critical importance to Canada. The Academy is an independent, self-governing, and not-for-profit organization established in 1987 and is one of the 3 national academies that make up the Council of Canadian Academies. We have over 800 fellows from across Canada, all of whom have made significant contributions to engineering in Canada in the private, public, and academic sectors. I should mention that the views and opinions being expressed here are those of the speakers and myself, and do not necessarily reflect the official policy or position of the Academy. Having said that, the Academy has identified net zero as a top priority and is in process of forming a net zero task force to assess and evaluate potential engineering solutions in achieving net zero by 2050 while enabling economic prosperity. The webinar series is actually the main tool for broadly disseminating the learnings from work of the task force. I invite all of you to provide your views and share expertise with the task force. Before starting, I would like to go over a few housekeeping items and explain the format of our online proceedings. I'm sure many of you have attended past webinars and you probably know that you are muted. If you have a question, anytime during the presentations, we invite you to use the chat option, which is found at the bottom of your screen, and then we will do our best to answer your questions. For your information, this session is being recorded and will be available on our website. We have 2 presentations for you today. After the presentations, I will open the floor to answer your questions. Finally, I will ask each panelist to provide their concluding remarks for 1 minute. Now, let's get started with my remarks. Currently, 8 countries have passed legislations to achieve net zero by 2050. 7 countries are in process of signing legislations. 11 countries, including Canada, are in process of developing policies, and several countries are in discussion. Our objectives are to assess various pathways in terms of their technical and technological soundness, economic impacts, challenges, and their potential in achieving net zero emissions by 2050. Given the fact that Canada is in the stage of policy evaluation, assessing various pathways to net zero is very timely. Canada has a wealth of diverse and also world-class resources, from hydrocarbon to hydrogen to nuclear, ocean, solar, wind, and many more. So unlike many countries around the world, we have numerous pathways to achieve net zero, and electrification has been mentioned by the International Energy Agency, IEA, as an important pathway that's being pursued by many countries. As a matter of fact, more than 15 countries have announced their plan to ban the sale of gasoline and or diesel cars, with varied kickstarts that some of them actually starts very soon. According to IEA, electrification and electricity gains in behavior change are central to achieving net zero. The IEA is forecasting that electrification based on low emissions electricity will drive the charge, where over $2.2 trillion per year will be spent to make this happen. We in Canada have been blessed with low emissions electricity. As you know, 82% of our electricity is low emissions, 60% is from hydro, 7% from other renewables, and 15% from nuclear. The remaining 18% is from coal and natural gas. If we shift from gasoline to diesel transportation to electric cars and decide to use more electricity for industrial and residential use, this could increase electricity consumption by 250%, which begs the following questions. What stick or carrot policies can bring behavior changes to improve consumers' energy efficiencies? What needs to be done to find the best combination of low emission energy sources, renewables, hydro, nuclear, natural gas, options in meeting the increased demand? What are the challenges and roadblocks associated with expanding grid capacity across Canada and North America to connect everything together, so we won't have we can overcome some of the challenges that we have seen recently? What is the future of the automotive industry in Canada, given the big changes happening south of the border with Biden and his new policies and his new approaches? Above all, what is the role of engineering in moving forward with this big change? Canada is blessed with world-renowned, creative, innovative, inventive, intelligent, and gifted engineers, and the combination of natural and human resources is next to none. Canadian engineers can lead the world in using innovation and new technologies to find economic solutions to create a smart, robust, reliable grid for transmission across Canada and North America, along east-west and north-south axes, with innovative power storage solutions to help us overcome the variability of solar, wind power, or extreme weather, or other unforeseen situation, such as what we have seen and witnessed in Texas. This could mean finding breakthrough technologies by solving the storage challenges for wind and solar energy and others, perhaps by storing hydropower by compressed air, hydrogen generation using electrolysis, pumped hydropower into a retained pool behind a dam, using flywheels, storing compressed air underwater, and using high temperature gas reactors. I'm hoping through this series of dedicated webinars to net zero emissions, we can get you engaged, connect ideas, people, and projects, and make a small contribution to achieving net zero. On that note, it is my pleasure to introduce the first distinguished speaker, Dr. Peter Frise. Peter, CAE, FECPeng, is a mechanical engineer educated at Queen's and Carleton universities. He has worked at Schlumberger and Husky. Peter's academic career has included posts at Carleton and Windsor, where he held the Chrysler NSERC Senior Industrial Research Chair in Mechanical Design. He founded Canada's first university program in automotive engineering in 1998, and in 2000, he was elected to lead the Auto 21 NCE, which supported more than $150 million in applied research for Canada automotive sector. Peter will talk about the role of electric autonomous vehicle in achieving net zero and the future of the Canadian automotive industry. So please join me in welcoming Peter to deliver his presentation. Peter, you have the floor.
Very good. Well, thank you very much, everyone. It's a real pleasure to be here. It's a real pleasure to be anywhere these days, isn't it? It'd be much more fun if we could be somewhere other than where we always are, which is, anyway, it's COVID, so here we all are. I'm going to just get into this. My talk will, there we go. And can everybody see that okay? Can somebody give me a thumbs up? Good. Okay. So my talk will really talk about the automotive industry, how it works, why it does certain things and doesn't do certain other things. So it's a very exciting and dynamic business sector, and that's the key thing. It is a business sector. It's not something that governments run, but it's something that governments influence. It's mostly influenced by consumers, and I'll talk about other factors that play into how the auto industry makes decisions. So let's get on with it. Okay, this is interesting. There. Okay, so it's a big world out there, as you can see. There's lots of different kinds of vehicles out there, and lots of some older ones, some new ones, big ones, small ones, and all that. And I'm sure, like me, most of you at one point have said to themselves, why doesn't the car industry build the kind of vehicle I want to buy? Why don't they build the perfect vehicle for me? Well, there's always a reason for these things, and here they are. There are three things that the auto industry has to respond to. It must obviously respond to government demands for regulatory compliance with safety and vehicle emission standards and so on. And the government is chiefly interested in energy security, environmental improvements, safety improvements, and good jobs. The auto industry is a huge provider of good jobs. So every government in the world tries to attract a strong auto industry. The other set of imperatives that the industry has to deal with are consumer desires. What kind of car do people want to buy? Basically, you can sum that all up in what's called the value proposition. The value proposition is where you divide performance by price. Now, we're all engineers, so when you look at that, it's kind of a lumpy equation. It doesn't really work out from a standpoint of units and dimensions and so on. But if you sort of do it conceptually, if you divide however you decide performance priorities are, quality, on-road performance, fuel economy, safety, fun to drive, cool features, goes around corners fast, pull my boat to the cottage, all those things. Divide by price, you have a value proposition. So that's really how consumers decide what kind of vehicle they want to buy. And then, of course, there are industry imperatives, which are largely invisible to the consumer and largely invisible to the government, quite honestly. but they're there. They are really important. The car industry basically has to build the highest quality vehicles it can at the lowest possible cost to maximize profit. They have to do it quickly because the market shifts and changes. They have to have factories that are efficient, have a good supply of workers and good logistics arrangements and all that sort of thing. And all of that has to be layered on top of regulatory compliance, which is a challenge. So this is a very difficult balance. Designing a new vehicle is a complex balance among all these factors: energy efficiency and environmental, safety, performance, creature comforts, the sound capacity, how much noise the car makes inside, its ability to tow, how easily can it be made, serviceability, and cost. These factors all have to be balanced. And of course, as engineers, this is our life. We have to balance different factors and make sure that we are properly meeting the needs of our customers. So we're going to talk about a new term that's been coined: automobility. What is it? Automobility is the secure zero-emission movement of people, goods, and services using advanced information technologies. Automobility, we're sort of moving from the automotive industry to the automobility industry. And it's a symbolic word, and it's symbolic of a big change in technology. To a large extent, if you go out to your driveway, the car that's sitting there, unless it's one of the few, relatively few electric vehicles that are around, that car is fundamentally not different from a vehicle that was built 50 years ago or even 70 years ago. It has four wheels, it has an internal combustion engine, it has a transmission, body's made of steel, and so on and so forth. But the future vehicle is really going to be quite a different beast. And so people are starting to use this term automobility to symbolize that transformation. To achieve this automobility, clean, secure, safe movement of vehicles and people and goods, we're going to adopt 4 technologies. And the acronym that the auto industry is using is CASE, C-A-S-E, connected, autonomous, safe and secure. Some people use shared, but I'll talk about that briefly in a moment, and electrified. Connected, autonomous, safe, secure, and shared, and electrified. Now, shared. All this changed about a year ago, obviously, when COVID came along, and I think most of us would agree that the thought of getting into a shared vehicle with a bunch of strangers is probably not something we'd be very comfortable with right now. But the notion of safe and secure sort of encompasses the concerns about health as well as road safety and software security, which is crucial to these vehicles. So let's dig into this and have a look. Okay, so if you look at what kind of improvements have been made in 30 years, the 2 vehicles I could find which are most comparable, and there are lots of others, I guess, a 1988 Ford Escort and a 2018 Ford Focus. Small, 4-cylinder, 4-person car, transverse engine, and so on. And if you look at the statistics, you can see a huge increase in weight. The Focus weighs 42% more than the Escort did, but it's twice as fast in a 0 to 60 time, and it gets about 45% better fuel economy. Plus, it has all these features: fuel injection and airbags and ABS brakes and air conditioning, all that stuff. How did the auto industry do that? Well, you and I. It's engineering. That's how it was done. It wasn't easy, but it was done. And the auto industry continues to improve. When I give a talk like this in a public place, I always ask the crowd, put up your hand if your car has not started in the last year. And about 90% of the time, no hands go up. And I can tell you right now, if this were the 60s or 70s when I was learning to drive, every hand would go up. Modern cars are incredibly safe. They're much, much cleaner than previous generations of vehicles, but that isn't enough. What has to change? Everything. Everything will change. But some things will kind of stay the same too, and we'll get into that as well. But to meet the regulatory changes that the government is demanding and satisfy the consumer market, almost everything will change in some way. So let's talk about material and body structures. This is not just to talk about electrification, although we will get into that. But if you think about a car, there's a lot more to a car than just an electric motor or an internal combustion engine. So materials and body structures. I only have one slide on this, but if you look at it, you can see that between 1985 and 2010, which is 25 years, the materials that went into a car really didn't change very much. Most of it was ferrous metal, which of course is steel and iron, non-ferrous metals, aluminum, copper, brass, things like that, magnesium, plastics, rubber, glass, fluids, and other. In 2030, that could not possibly be the case. And you've already started to see that. You know, Ford advertises their aluminum body F-150. That is a big deal. The F-150 is the largest production light truck in the world. They make 800,000 of those a year at about 4 or 5 different factories. And they completely changed the material, which meant changing all the manufacturing processes, all the heat treating, how the materials are joined to each other, but also how they're joined to the rest of the vehicle, because the chassis of the vehicle and the suspension components are all steel. And of course, as engineers, we know that if you put 2 dissimilar metals together and you get them wet, you have a battery, then you have a lot of corrosion, and that can't happen. So, you know, vehicles like the F-150 and other vehicles which are using a lot of aluminum, that's going to become a more common thing, which is great for Canada, because we're a big producer of aluminum, especially up in Quebec in the Saguenay Valley. It's a very exciting opportunity. And I know that Christian's going to talk about the electric power system, and that'll play a big role in all of that. What about powertrains? How to make the car go down the road? Well, Canadian EV sales are picking up. You can see that in the curve. But you need to remember that they're really still only about 3% only about 3% of total vehicle sales right now. So for 97% of the vehicle market as of a year or so ago, an electric vehicle was not the option they chose. The other thing to always keep in mind is cars live a long time. The average age of a car in a North American road is between 10 and 11 years. So to replace half the cars on the road will take, you know, approximately 10 or 11 years. That's a long time. 10 or 11 years from now will be 2031 or 2032. So just because a new technology is available now, that doesn't mean it's going to be everywhere quickly. What about batteries? Well, I'm not an expert in batteries. I think Christian may have some things to say about that, and there are a lot of people around, or you know, a few people around who know a lot about batteries. But I'll tell you one thing, batteries are expensive, they tend to be heavy, and they can't store very much energy. But the biggest problem is the materials. One of the key materials, aside from lithium itself, is cobalt. And 68% of the world's cobalt comes from one place, the Democratic Republic of the Congo. And the problem with that is that it's far away from all the manufacturing centers. It's got some political stability problems, and the logistics of shipping huge volumes of material in and out of there are not simple. So there's a great deal of effort going on to establish other sources of key materials like lithium and cobalt. But until that is done, the price of batteries is going to continue to stay high. It's coming down, people are working on it, but it's a very, very difficult problem. And as you know, the second largest country in the world, we have a great deal of these materials in our country. The trick is to be able to recover them economically and have our country benefit from that effort. So you'll see more of that. Here's an interesting chart. It's a bit of an eye chart. I apologize for that, but if you focus on the arrow on the side, you'll see what the real problem is with batteries. Down the left side are some numbers. That's kilowatt hours per kilogram. That's energy storage capacity, or energy density, if you like. At the top are liquid fuels like gasoline, diesel, and so on. Then there are different kinds of diesel. Then you get into the gaseous fuels, biofuels like ethanol, and then coal, and then natural gas, hydrogen, and finally batteries. Look at the difference in energy capacity between diesel and batteries. It's just a whole order of magnitude, 2 orders of magnitude, really. And so what that means is that to build a vehicle big enough to pull a boat to a cottage or to haul a semi-trailer down the highway that weighed 80,000 pounds, you're going to need a lot of batteries, and they're heavy and they're expensive. And that chart right there really tells the story of why electric vehicles are not the choice for most consumers today. But they will be. But this is the problem right here. It's energy density and cost and weight and so on. Now, how many vehicles will be electric powered in the future? This is a very interesting chart from my friends at Schaeffler Technologies, which is a very large German automotive supplier. And if you stare at it, I think you'll understand. In 2030, which is about 9 or 10 model years away, the global market will be about 30% internal combustion engine strictly, and about 30% battery electric only, and about 40% HEV, hybrid electric vehicle. So what that means is that 70% of global vehicles will still have an internal combustion engine, and 70% of global vehicles will be at least partially electric powered. So what you're going to see, and I think this will be a recurring theme in this seminar or webinar, is that you will see it'll be a mix. There won't be just one solution. There will be a transition period when things will change rather slowly, and then the new technology will take over. But it'll take longer than people think. In the U.S. market, about 74% of the vehicles will still have an internal combustion engine, and about 62 will have electric power, partial electric power. But that's how the mix is going to be. So it's not easy to draw a line between an internal combustion engine vehicle and an electric vehicle. There will be a bit of a mix in the middle, and that's just how it's going to be. Autonomous cars. Now, this is the one everybody wants to talk about, and it is very interesting and very exciting world coming along. But as an engineer who works with the auto industry, it makes my head hurt when I think of some of the possibilities. So I'm not going to spend a lot of time talking about autonomous cars. I'm going to spend some time talking about what can go wrong with them. And I think that as engineers, we have to be prepared, because it's our job to protect the public where technology is concerned. 94% of all crashes are due to driver error or misconduct. We've all seen some nitwit driving too fast on the highway, or tailgating, or doing something silly. 94% of all crashes are, the nut behind the wheel is the problem. How do we protect everyone from that person? Well, this is a chart from the SAE, the Society of Automotive Engineers, excuse me, and it really lays out the spectrum of how we will get from the sort of no technology cars of a few years ago to a full autonomous vehicle. So I'll go through them rather quickly. A human-only vehicle, like let's say a 1968 Corvette, it doesn't have cruise control. You get in the car, you start it, you drive it. If you choose to drive it into a wall, it will hit the wall. The car doesn't do anything to protect itself. A modern vehicle is a level 1 vehicle, and some functions can be done automatically, like, say, cruise control. So you can set the speed at 60 miles an hour on the highway, and the car will do 60 miles an hour. Now, again, if you choose to drive into a wall, you will hit the wall at 60 miles an hour. A level 2 vehicle has 2 functions that are automated, maybe cruise control and lane keeping. And you're starting to see a lot of this now. Many, many vehicles are level 2 vehicles today if you buy a brand new vehicle today. And they can do 2 things. A level 3 vehicle has partial autonomy. Now, I have to tell you, as an automotive engineer, level 3 vehicles scare the heck out of me. I never, ever, ever want to be in one, and I don't want them on the road because they can operate autonomously until they don't, and then they just crash into something. And so the idea is the driver has to constantly monitor what the vehicle is doing and be ready to take over. But people don't do that. And you've seen that with Tesla vehicles driving into fire trucks and going under tractor trailers and so on. Level 3 vehicles are bad news. They're a step along the way, but in my estimation, they should always be an R&D project and not a consumer product. Oh, I got these crazy. Okay, sorry. Level 4 vehicles, the vehicle can do everything by itself, or you can take over if you wish, but you don't have to. The vehicle is fully capable of doing things, driving by itself. And level 5 vehicles, there's no steering wheel, there's no pedals. You get in, you tell it where you want to go, and off you go. If the vehicle malfunctions, you're going to get hurt. So that's how the SAE has defined it. I think it makes sense. It's all fine until something goes wrong, and then you have this. So let's not go there. Now, what can go wrong? Well, hackers can get into cars, and if you type in, I think the title is on YouTube, Jeep Hacked. You'll see a really scary video of two guys sitting in an apartment who took over a Jeep, and they drove it around a parking lot with a person in the car, and the person could not stop the car, could not make the car do what he wanted it to do. They could steer it, they could drive it, they could turn the wipers and heater on and off, and they could control the brakes. And there's lots of ways into a modern car. The Bluetooth phone, built-in Wi-Fi systems, the keyless entry system is a wireless system that can be hacked, remote car starters, etc., etc. Even the tire pressure monitoring system can be hacked, and they have been. So, you know, you just can imagine what would happen if somebody hacked into every police car in a city. It'd be a great time to rob a bank. Here are the kinds of sensor arrays that an autonomous car will have to have. It'll have to have long-range sensors for adaptive cruise control to keep distance from the vehicle in front, short-range sensors for parking assist, for pedestrian recognition and things like that, sensors at the side, sensors at the back, sensors all over the place. And they're different kinds of sensors. There'll be long-range radar, LiDAR, or, you know, cameras, short range and medium range radar, possibly some ultrasonics. Each one of these kinds of sensors has got strengths and weaknesses, and somehow you have to fuse all of this information together, create a driver awareness picture so that the person who's in charge of the vehicle has awareness of what's going on, and you got to keep the vehicle safe and moving, and you've got to do it in an environment which is constantly changing, and some of the other vehicles on the road are not autonomous. So they won't necessarily act rationally. They may have some crazy person at the wheel who just wants to do his own thing. So it's an extraordinarily complicated environment, and that's why it's going to take a while. Cars will become very, very expensive. They're already getting expensive. The average transaction price of a modern vehicle in a new purchase in Canada, I think, is $38,000. I think they're going to get a lot more expensive than that when you look at the level of technology that has to be on them. They will also become much harder to build. There's a lot of electronics in a car now, and there's going to be far more going forward. Huge amounts of software, very large numbers of microprocessors, and computing power will be required. It'll have to be redundant. It'll have to be safe and secure. This stuff is not easy to do, not on the scale that the auto industry builds. Just to give you an idea, today in my city, in Windsor, Ontario, Chrysler will build, or Stellantis will build about 1,000 Chrysler Pacifica minivans, 1,000. So that means they have to have 1,000 windshields, 4,000 tires, you know, 1,000 engines, 1,000 transmissions, 1,000 sets of wiring, and all that. And tomorrow they'll build another 1,000 vehicles. So it's an extraordinarily large industry. And just because some professor in some university can make something work on a little test track, that doesn't mean that industry can build it at an economic scale in the numbers required. So again, complicated job, going to take a while. What about ownership of vehicles? That's going to change too. You've got Uber and Zipcar and all the shared ownership models, as well as actual shared vehicles. How is all that going to be affected by COVID-19 and the ongoing concerns about pandemics? And again, automakers, they have to know, they have to understand this stuff, because they have to build the vehicles that people want to buy. And it takes 3 or 4 years to design a new vehicle. So if social things change quickly, they've got to somehow respond to that. So this is Dr. Dieter Zetsche. Dr. Zetsche is the president, or is the chairman of the board of Mercedes-Benz. And he said a year or two ago this: electric mobility and autonomous vehicles are like a bottle of ketchup. You know that something is coming, but when will it arrive? And I think that's exactly the right way to think about this. I can't tell you. I don't know exactly. I can guess, and other people might have other guesses, but I'll tell you one thing: it's going to take longer than most people think. So where has all this left the auto industry, and how will it affect our country? Well, I think there's a few things you've got to sort of keep in mind here. Future vehicles, that is a pain. Sorry, I'm sorry about those. Future vehicles will have much more complex electronics and software systems. They'll have much less routine maintenance. There won't be very many fluids on the car, no gasoline, no oil, things like that. Windshield washer, antifreeze, and possibly brake fluid, but maybe the brakes will be electric. There'll be no air filters or oil filters to change. Tires probably will last longer, and so on. There'll be no transmission, no complicated transmission, just a very simple gearbox from the electric motor to the wheels, and many fewer moving parts. So if you're working for a company that makes all those moving parts, pistons and gears and all that stuff, you have to look for a new business model, not for next year, but for the next decade. But cars will still have a body structure, wheels, windscreens, wipers, infotainment, HVAC systems, and autonomous vehicles will only be a small percentage of the road for at least another decade or more. The future car will still be a car. And, you'll hear politicians and journalists and so on say, oh, the car industry is going to change. Everything's changed. We have to throw everything away. It's all software and electrical stuff now. Don't worry about any of this other mechanical stuff. Sorry, not true. If you want to get into a car and go to your Aunt Mary's house, you're going to need 4 wheels, a suspension, a powertrain, some brakes, a vehicle structure, some seats, a windscreen. You want to be warm, so you need an HVAC system, and so on. All the things that are on a modern car will be on the future car, plus some extra stuff. And that's a very exciting opportunity. But don't let anybody tell you that we can just throw everything we have away now. That would be a huge mistake. What we have now provides jobs for a couple of 100,000 Canadians, and prosperity all the way across the country, especially in my part of the country in Southern Ontario. So, the future car will still need all of those things, plus some more things. The trick is, how can we get a piece of that new action? The fact is, we build most of that stuff now. Here in Windsor, we have one of the best tool and die sectors in the world. Well, do we need tools and dies and molds in the future? Well, yeah, because a car still will have a body and it has to be stamped out of metal. So somebody's going to have to make the molds and dies for that, and the automation lines and the vision systems for factories and all those sorts of things. So the world is not going to throw all that away. But it will take a strong, determined effort on a large scale, and it'll have to be sustained for many years for Canada to continue to play a big role in this industry. And so, just a small commercial, we are presently we did Canada's first university level program in automotive engineering in 1998, and we're developing a new program to give young engineers the opportunity to contribute to the net zero revolution and provide the necessary human resources to allow our country to take part in that. And there'll be more details to follow. So watch the University of Windsor I think I can say confidently, we know what we're doing and we're preparing for the future. We're prepared for the future and we're moving forward with that. And I guess that's all I have for you. So I'd be happy to answer any questions, and I hope you enjoyed my talk. Thank you.
Well, Peter, thank you very much. It was very informative, thought-provoking. So we are gonna wait for the second presentation before we open the floor for answering questions. So I would like to now talk about the next presentation, which is about the challenges and opportunities of electrification in achieving net zero, but looking at it from the Quebec's context and perspective. And this will be delivered by our distinguished presenter, Dr. Christian Bélanger. Christian joined Hydro-Québec's Research Institute in 2016. He's currently Director of Research, Strategic and cross-functional projects. Prior to joining Hydro-Québec, he worked in research and development in various organizations in the chemical, materials, and automotive sectors, both in Europe and in Canada. He has extensive experience in innovation management in both the public and private sectors. His PhD is from McGill University in chemical engineering. His engineering degree in physical engineering is from École Polytechnique de Montréal from 1986. He owns an EMBA from Concordia University. So I would appreciate if you guys join me in welcoming Christian to deliver his presentation. Sir, you have the floor.
So thank you very much, Soheil, for the introduction. Do you see my screen now?
Yeah, I can see it and I can hear you well.
Okay. So what I'm going to talk today is more electrification in general, including transportation. So during my talk, I will, as much as possible, when transportation is involved, give you a few things regarding it. So my talk today I will start by talking about the challenge utilities are facing today into energy transition. The challenge we face also in CO2 emission reduction, and what is efficient electrification, and where and how, I mean, EV or hybrid EV can play a role in this. More generally, what are the potential electro-technology for direct electrification that can be used to decarbonize our economy, and what is the role of innovation in this, let's say, achieving net zero economy by 2050? So today, electric power business are really facing big challenge. Maybe you're not aware, but these are very capital intensive business. Hydro-Québec, for example, is a 70 billion asset on book activities. These grids are designed for peak demands. So basically they are over designed, and half of the time we use the grid to let's say half of its capacity. So which means that we're not using the overall asset. Most of the electric power business are owned by taxpayer, and I mean, rate is not necessarily representative of the cost. And depending on where you are, I mean, the source of electricity can be clean, or sometimes it's not the case. In fact, Soheil, in his introduction, mentioned that in Canada, you have like 65% of our electricity sources, which is from hydro, which is not the case if you go south the border. It's more the opposite. You have about 60% of the electricity which comes from, let's say, gas and coal, which is a completely different picture if you want to electrify your economy. And in particular, if you want to, let's say, introduce electric vehicle, sometimes it can be worse if your source of electricity is not green, or if it's not low emission, for example. And the main challenge we're facing also is that we have to adapt very quickly the grids, because if we want to reach the, let's say, the goal of reducing our emission and electrify our economy, grid will need to adapt very, very rapidly. There's 4 drivers for the energy transition. In fact, the first one I just mentioned, it is decarbonation. I mean, if we want to reach the, let's say, Paris Agreement of avoiding it, let's say, an increase in temperature below, let's say, 2 degrees C, we need to accelerate the decarbonation of our economy. The other driver is decentralization. But what I mean by decentralization here is that a lot of, let's say, new source of intermittent energy will be decentralized. So you will have customer, you will have you know, a small industry that will have their own or that production of electricity connected to the grid, and this will have also an impact. Democratization is another a very important point, because a customer will play a very important role into the future of the grids. And what I mean here is that, you know, the customer load will be connected to the grid and will be controlled also by the grid. So that's where, I mean, customer behavior will be extremely important. And I would say the last driver is digitalization, because you cannot do that without digitalization. For example, in your home, with the Internet of Things, I mean, utilities, if you agree, will be able to control your heating system, your you know, lighting system, and everything you will agree on. So this is also a very important driver. And all this is going to disrupt the electric system. And again, electrification, you know, we'll look at EV vehicle, smart changing, heat pump, all this technology, which have decreasing costs, will have an impact on the electrification. Decentralization also, you have key technology like you know, solar PV on homes, batteries in home, very small microgrids. All this will impact the grids. And again, the digitalization with smart metering, remote control, you know, beyond the meter application, you know, future grid will need to take all this into account, and you will have to be, you know, very proactive in order that to reduce the risk of integrating all these technology on the grid. Now let's talk about greenhouse gas emission in Quebec. So in Quebec today, we are close to 80 million tons of CO2 emitted. Basically, it's about 10 tons per capita. Which is one of the lowest in North America, and you understand maybe a little bit in the next slide why. Because if you look at the chart on the right side of the screen, I mean, you know, you see that electricity is a very low emitting in terms of CO2 in Quebec, because I would say almost 100% of our production is green. Transportation represent about 43% of our emission, and you can divide it by, let's say, that 43% is maybe like 22-23% is light vehicle, and the rest is heavy vehicle. And industry represent another 30%, and then you have residential and commercial, which is about 10% of our emission. So about Hydro-Québec, as I mentioned in the previous slide, you've seen that electricity production in Quebec was extremely low in terms of CO2 emission. And this is explained by the graph. If you look at, if you do, let's say, life cycle analysis, and if you compare different sources of electricity, if you have, let's say, hydropower run of a river or hydropower by a reservoir, which is the most important part of hydropower we have in Quebec. So basically you are at around 15 grams of CO2 emission per kilowatt hour. If you compare it with other sources of electricity, for example, wind, which is about the same than hydropower, you are at 14. If you then look at PV, you're maybe a little bit more, 4 times more than the hydropower. So we're lucky enough here to have, let's say, almost 100% very clean electricity. And in Quebec, we produce about 210 terawatt hour per year, and about 175 are used in Quebec. The rest is exported. Quebec has a target of, let's say, reducing its CO2 emission by, let's say, 37.5% from the 1990 base by 2030. And then it has a goal of, let's say, 80 to 85% of emission reduction by 2050, which is extremely aggressive targets. And if we don't do nothing, which is the, let's say, the black line on the screen, we will see an increase in terms of CO2 emission. And if we don't do nothing but let's say, CO2 tax increase, we're going to see a slight decrease in terms of emission, but not enough to reach, the goal of 2050. So how could Quebec in 2050? So on the left side of the screen, you have Quebec's today. So basically you have electricity, which is clean, which is about 36% of our energy consumption. We use biomass mainly in the pulp and paper industry, and the rest is from fossil fuel. So basically you have about 56% of our energy, which is fossil fuel based today. I would look at Quebec in 2050 if we were to, let's say, eliminate fossil fuel. Basically, you would have electrification of transportation by about 37%. We would use electro technology, and I'll get back later on the next slide on this topic. We expect that we would have energy efficiency also, like for better insulation of buildings and so on, and using more efficient technology like thermopumps. And we also expect that we will need, you cannot electrify everything directly. So you will need also a green, let's say, fuel like hydrogen or synthetic fuel for some industry and process, and I'll talk about this later in the next slides. So basically, if you look at it from, there's a lot of number on that screen, but the main things to retain is that we have about today 275 terawatt hour of thermal energy, which is based on fuel. And let's see if you apply an efficiency coefficient by converting this energy fuel with electricity, the minimum, and if you apply the coefficient of 3, the minimum you will need is at least 100 terawatt hour of electricity, which is really aggressive and optimistic. A more realistic number would probably be 150 terawatt hour that you would need to completely electrify our economy, which means you would need to build in the next 30 years as much power as we've built over the last 100 years. So which is a major challenge. So that's where comes what we call efficient electrification, and this is an APRI based on it comes from APRI. So basically, what it means, efficient electrification, it's a win-win-win situation. I mean, the customer is winning, the society is winning, and utility is winning, and we're partnering in this to get let's say a lower carbon footprint of our economy. And so how do we apply that? So the first thing you have to do is to look at electrify as much as possible. So converting, for example, a gasoline car to an electric car is considered as let's say direct electrification, and it is also efficient in terms of energy. And in fact, basically you have a factor of 2. And if you cannot do that, the next step you have to look at is use let's say a green fuel. It can be hydrogen or a green synthetic fuel. And if you cannot apply that to your process, the last thing you have to do is maybe carbon capture and sequestration. So you have to look at all the application and go through that strategy for electrification. We've listed a list of, let's say, 50 technologies and indicators that you need to follow to build your electrification strategies. I'm not going to go through that list because there's a lot of things, but let's say electric vehicle are part of it. Low temperature thermopump, high temperature thermopump, geothermal, and you need to look also at different, let's say, green chemistry like ethanol, methanol, ammoniac. All this, you need to look at it as a way to, let's say, electrify your economy. And once you have that list of things, you need to take in, to develop business case for each of them. You need to take into account the evolution of cost of electricity, OPEX and CAPEX of electrification technology, evolution of carbon taxes, and the regulation. And then you need to build models, technology by technologies. And if I look at the next slide where we have, let's say, a rating of some of the technologies, first things you have to look is, let's say, the performance of the technology, which is, let's say, ton of CO2 avoided or reduced by terawatt hour. And you see on the graphic on the left side that EV are by far the most efficient, let's say, way to reduce your emission. Then comes, let's say, thermopump, and on third comes fuel cell vehicle. And you need also to look at your business case to take into account the cost of your electricity and look at it over time, because over time the cost of technology is going to decrease, CO2 tax may increase, and so on. So at one point, this technology will have a positive business case, and you need to look at it over time and by technology to develop your strategies for decarbonation of your economy. If you look at thermal consumption in the industry, so on this graph, what you see is depending on the process temperature, you see that the industry cover a wide range of temperature. It goes from low temperature, let's say about 0 to 100 degrees C, up to 1500 degrees C. So not all electrotechnology will be can be used depending on the temperature of your process. So on the lower side of the temperature, you have let's say low temperature thermopump that can be used, and then high temperature thermopump from, let's say, 100 to 200 degrees C. But when you reach to, let's say, above 100 and above 1000 degrees C, you will need to use fuel. And that's where, let's say, hydrogen or synthetic fuel can be used for processes that require very high temperature. And you will need this, and we call it indirect, in fact, electrification. This is an example of, let's say, increase in terms of electrotechnology in US. You have a list of 10 here electrotechnology that have been used in the industry from, and you see the increase from 2015 to 2020. I'm not going to go through that list, but what gives you, what it shows is that there's a lot of potential for electrotechnologies for the decarbonation of our economies. Example of R&D activities that we do is that you know, we have a pilot project going on now with a large thermal pump, 2 megawatt for large building to replace fossil, and so this is a demo, but you know, and we do that to show that the business case is positive. Another type of electrotechnology we're working is a wood drying microwave, for example, for the wood industry. Also, a type of R&D activity we do is a simulation tool for you know, grid friendly planning and operation for the integration of load. When I say load here, I'm also thinking of the customer load, so that they can be you know, monitored and operated by the grids. So these are very important activities for you know, for the expansion of the grid in the future. Example of the project we have with the large thermal pump, you know, the federal government has a goal of having by 2030 most of its building net zero, and so the we have in Quebec like 30 federal government building, and we hope that the pilot we're doing, all the thermal pump technology will be integrated in the retrofit of these buildings. And it's a real example of a win-win-win situation that I mentioned earlier for efficient electrification. So in summary, you know, identify electrotechnology with the best business case. You have to look at each of these technologies, where they fit in the market, and develop your business plan. You need utilities will need to establish partnerships so for the implementation of these technology. And least but not the least is that you need to plan your future near, because as I mentioned, you know, if we want to get to a net zero economy by 2050, we'll need as much energy as we use today. So we will need to increase by 100% our production of energy, which is an extremely big challenge. So thank you.
Many thanks, Christian. It was a great presentation. I really enjoyed all of the strategies and considerations and challenges, etc. I think it really gave us a great picture. I would like to now open the floor to receive questions from our audience. I would appreciate if you, again, as I mentioned earlier, use the chat box that it's at the bottom of your screen to pose your questions. I would like to maybe start with a couple of questions. I think that actually I would appreciate both of you answering, but maybe from different perspective. So maybe Peter, the first question is, you are talking about numerous barriers to adoption of electric cars, autonomous cars, etc. And then you mentioned, of course, all of these cars that we have already purchased, they are sitting there and people are using them. So that would be potentially one barrier. What are those barriers that you can see that really affecting this, slowing the acceleration of adopting electric cars and autonomous vehicles, etc.? And then the second question is, what government strategies or policies could accelerate actually adoption?
Well, I think there's a couple of different sort of distinct barriers to the adoption of electric cars. One of the key ones is affordability. Electric cars are, and the price is coming down significantly, but they are still more expensive than conventional cars, IC engine cars. Now, some of that affordability gap is being addressed with government subsidies, but to be perfectly honest with you, if you want some of my money to help you buy an electric car, I want some of your money to help me buy a new motorcycle. And I think that there's only so much that governments can do in simply giving money away to people. It is a strategy to kickstart things, but I don't think it's a sustainable long-term strategy. So there's an affordability barrier. And again, engineers are very good at bringing new technology to the market and reducing its price. That's what we do. The other one is performance of the vehicles themselves. And they're, again, they're certainly much, much improved from what they were before, but there are still gaps. And the problem of people who need a large vehicle, tradespeople, people who have cottages and want to pull a boat up to the cottage and so on, you really can't do that with an electric vehicle at the present time. They don't have enough onboard storage, energy storage capacity, and so on. So those issues are all being worked on, but those are the key barriers at the present time. In terms of one of the key things will be to increase the supply of the strategic raw materials that are needed to build the batteries. Lithium, cobalt, the magic pixie dust that keeps the batteries thermally stable. There's a whole mix of rare earth elements in there. And the fact of the matter is, unfortunately, at the present time, most of those materials come from places that are not politically stable. Some of them aren't even friendly towards us. And we have those materials within our country, but we don't have economic supplies of them and economic means of recovering them. In terms of autonomous vehicles, what are the barriers? Well, a lot of it is technology, the amount of software and computing power required to make these things safe, the affordability of the sensors and all the other hardware on board is a big problem at the present time. And there are sociological barriers. A lot of people just don't trust technology enough to entrust their family to it and their own lives. And I think there's some justification for that. I think we will go through some rough times with technology before it becomes as reliable as I think most people feel it needs to be. There are also issues around insurance. If the car malfunctions and crashes, who pays? Whose fault is it? Is it the car company's fault? Is it the fault of the sensor company? The fault of the company that made the software, if that happens to be a third party? Is it the fault of the infrastructure, or is it the fault of the driver of the car, or at least the operator of the car? But again, if you're driving a level 4 or level 5 vehicle on the SAE mobility spectrum, you're not in charge of the car. You get in the car, you set the destination, and the car chooses the route, and the car chooses the speed, and the car chooses what to do. And so I think society and the legal system have a lot of work to do as well. And one concern I have is that I think there have been some approvals of autonomous vehicle tests that are ahead of the technology, and that concerns me greatly. I don't want to be on the road with an autonomous vehicle right now. I don't think they're ready. Really, I don't. They're an excellent candidate for a test track at the present time.
Thank you, Peter.
Okay.
Christian, in your presentation, you talked about 3 options, and then in the order of priority, you mentioned electric cars, and then hydrogen, and then you mentioned sequestration of CO2 in that order. So my question is, what do you see in terms of barriers, in terms of electrification? Why? Because that was your preference in terms of the options that you looked at. So from your perspective, what do you see as challenges that would make that option not really moving ahead?
In fact, there's a lot of electro technologies that are out there, which are available, but their business case is not, let's say, positive. And to have let's say, a positive business case for these technology, including EVs, we estimate that the cost of CO2 per ton would have to be above, let's say, $250, $300 per year, which is, once we will reach that, there's a lot of electro technology that will becomes extremely interesting and I would say cost competitive. And that's one of the major issue, when you have a ton of CO2 at $30 or something like this, we're very far from, let's say, reaching let's say, interesting business case for these technology, because some technology are there, they are out there. But this varies from one country to another. If you go in Germany, where you have, if you include all the taxes on gas and the CO2, you have an equivalent of CO2 cost per ton above $400 or $450. So in this country, there's a lot of technology that makes sense. It's a lot more difficult for us here in Quebec. This is one of the main, I would say, a main barrier.
Okay, thank you very much. Actually, there was a follow-up question from the floor. They were wondering, when you were mentioning hydrogen, what would be the source of hydrogen? Where are you going to get it? Are you thinking of electrolysis?
Yeah, in Quebec, in fact, we expect, today let's say we consume about 100 kiloton of hydrogen per year. Mostly it's gray hydrogen, so mostly it comes from the cracking of gas, natural gas. And so Hydro-Québec has announced recently, in fact, that it's going to produce hydrogen in the near future. So we expect it from being hydro, or at least from renewable energy, which is today mostly hydroelectricity. We expect that by 2030, about, let's say, 1 gigawatt could be over, let's say, the 40 we have in Quebec could be used for hydrogen production, which represent about, let's say, 8-9 terawatt hour of electricity for production today that is around 210. So basically, we see it this, for the next 10 years, it would come from hydroelectricity.
Thanks, thank you very much. So this is a question for you, Peter. Is about battery capacity, and can that be realistically be increased by 3 times in the future? Because I think you mentioned that was one of the challenges, that you couldn't really use electrification for running big trucks, for moving items from point A to point B.
Well, okay, so there's 2 ways of looking at battery capacity. Well, there's, and again, I have to caution you, I'm not a battery expert. If you want to increase the range of a vehicle by a factor of 3, you obviously need, 3 times the battery material for a given technology. And the problem with that now is cost. Batteries are tremendously expensive. The battery is by far the most expensive single component of an electric vehicle. It probably costs as much as the rest of the vehicle combined. And so to think of tripling the cost of the battery, you'd basically be adding another 50% to the cost of a given vehicle. So, you know, a $40,000 vehicle would become a $60,000 vehicle. And you know, they're not affordable. The average transaction price of a car in Canada, I think this year's, I think it's about $38,000. So, you know, some people do spend $60,000 on a car, but the average consumer can't do that. And if the average consumer can't do it, that means they won't sell very many of them, and they won't have that many vehicles to amortize the cost of the R&D over. And so the math on all that just doesn't work. So, you know, anything can be done if you've got enough money. It's as Christian said, it's making a business case that is attractive, that makes sense. That's the problem.
And you know what, in my opinion, that's where we need to start evaluating and looking at the low-hanging fruit and looking at all of the challenges, opportunities, and technology comparison, etc. Following up on that question, this is for Christian, in terms of providing perspective on how quickly transport sector will be electrified in Quebec, for cars, for light duty vehicle, for heavy freight transport, for trucks and rail, etc.
So, in fact, in Quebec has the highest concentration of EV vehicle in Canada, and particularly, I would say, around Montreal. Recently, in fact, we probably are now at 70 or 80,000 EV vehicle on the road. And the Quebec government has announced last fall its green green plan, if you want. And basically, the goal is to have 1.5 million electric vehicle on the road by the end of in 10 years, so by 2030. And 1.5 million vehicle on the road is about 25% of the actual fleet, which is around 6 million. And the government is also targeting at 2.5 million by 2035, so which would be let's say 40% of the actual fleet, which is extremely aggressive. And as you're probably aware, in Quebec, you can get subsidies up to $13,000 per car, which is which is a lot of money. This is the current I would say situation for light vehicles. For AV trucks, I don't think we're probably looking more at fuel cell technology for large, let's say, AV trucks, and we expect probably by 2030 around 1% of let's say AV trucks using hydrogen on the road. So we're probably going to see like more or less pilot projects and things like this. So that gives you more or less a perspective of the electrification of, let's say, transportation in Quebec.
Yeah, and you know, I think that 30,000 subsidy that you mentioned, probably they did some evaluation, economic evaluation in terms of economic prosperity for Quebec to come up with that number. Because so the next question would be for both of you, but I'll start with Peter. That's about the strength of Canada's research and development in automotive industry. And actually what I would like to add personally to it is that car industry is extremely important for Canada. What are we doing to make sure that we are positioning ourselves? Because Peter, you mentioned there is this transition period that we are gonna go past. Things are not gonna happen overnight. So how do we position ourselves for capturing opportunity during this transition time or period, and also beyond that, when we are moving to just fast adoption of electric cars?
Well, I think it's important to understand that, and this can't be taken literally, but there is no such thing as a Canadian auto industry. There's a North American auto industry, there's a global auto industry, and there's the Canadian segment of the auto industry. And so the car companies don't do R&D for the sake of doing R&D. They do it because they need it for a future product. And so we have to find the niches, as always with Canada. We always have to find the niche that makes sense to do here. And it makes more sense to do it here than to do it somewhere else. And so we have developed a strong niche in lightweight materials, which again are very important for the future automobile. We have developed a strong niche in high power electric machinery. We have top-notch people in several different universities, and there are companies that do that kind of work sprinkled across the country, TM4 in Quebec, and there's some companies in Ontario and out west. And so I think what we need to do is to support those niches. And again, this goes back to my sort of second or third last slide. This is going to take a concerted, big scale, long-term, sustained effort on the part of governments, industry, and academia if we want to make a difference. And if we want to have a place in these things. We cannot do everything. There are very exciting initiatives afoot to make batteries in Canada, but that would only make sense if they can get a supply of the materials at a better price than they can get them elsewhere. Now, again, we have the second largest country in the world. Somewhere around here, there's got to be a lot of those materials. In fact, they are here. What we need to do is put a lot of effort into figuring out how to economically recover them and provide them to a manufacturer, and then the manufacturer will come here. But everything is done on a business case basis. It's not done based on emotion or nationalism or because they like the color of our eyes. You know, it's all done on a business case basis, and we have to make that business case, and we have to compete with everyone else while we do it.
Well, absolutely. I mean, to me, if we actually use innovation, then as you said, we are going to be able to get a bigger piece of the pie in terms of that North America auto industry in terms of business perspective. So, but then you are bang on in terms of collaboration with all levels. I mean, you can't just accept universities to do it themselves. You have to have government, you have to have policymakers, provincial governments, federal governments, etc., to work with us. So they are like 100% agree. So Christian, the question is for you that with this climate change, have you done any evaluation to see what would happen to water flow to dams, and is this going to have the climate change any impact on your business moving forward?
In fact, we're doing a lot of modeling of the impact, of the climate change on the, let's say, impact on the environment. And regarding water, in fact, we expect to have 10 to 15% more water in our, let's say, reservoir in the next, let's say, 40 years. So basically, we would expect more water than we have today. So, which is somehow kind of a good news. So.
Thank you very much. So this next question, I think, would be for both of you. It's about in the agricultural sector, which is using diesel for powering their equipment. For, you know, in the future, if you are talking about reducing greenhouse gas emissions, what options do we have in terms of replacing diesel?
Well, agriculture is one of those difficult sectors in a way because it requires very high levels of onboard power to operate a big piece of agricultural equipment. On the other hand, and again, you can't take this literally, but weight is much less of a concern because the vehicles don't go very fast and the distances that they travel are not very far. I know there are projects going on right now. I'm not at liberty to divulge where they're happening, but there are projects involving electrified tractors, electrified construction equipment, things like that. Those things are ongoing right now. One of my former grad students is the head of powertrain development for one of the largest engineering firms in Detroit. And he said his whole world has switched from IC engine to electrical in the last 2 or 3 years. And almost everything he's doing now is electrical. Now, as Christian said, I think that the key thing to understand is that a lot of that electrical mobility will be brought about by fuel cells. I think, for a large truck, trucks get paid by the ton that they haul down the road. And, if you're hauling 50,000 pounds of batteries in a truck that's licensed to weigh 80,000 pounds, you only have 30,000 pounds of payload. Well, that's what the customer's paying for. He's not paying to haul your batteries down the road. So to make a large truck or a big piece of agricultural equipment sort of make sense, I think that a fuel cell is the way to go. I did a big study a couple of years ago for a major automaker on the role of hydrogen in the future economy, and I think it is foundationally important. And you can use hydrogen for anything you can use any fuel of today in. You can run a steel mill with hydrogen. You can run a big ship, a city bus, a large highway truck, and so on. The key thing is to use the hydrogen intelligently, not in a combustion cell, not in a combustion engine for mobility, but as a fuel cell fuel. And I think that's probably where we're headed with agriculture as well. But it'll take a long time because, again, farm equipment lives a long time. Farmers have pretty thin profit margins, and that stuff is expensive to buy.
Thank you, Peter. Any
Well, I share Peter's point of view. I mean, a fuel cell is probably the way to go. But we are also looking at, let's say, synthetic fuel, like synthetic diesel that you could use into, let's say, these tractors. But we don't see a business case before, let's say, 2040 or 2045. So it's long. It's far down the road. We see business case for, let's say, these synthetics diesel for remote communities in northern Quebec or Canada, where they use diesel, and the cost of electricity is something like, I don't know, 30, 40, 50, sometimes $1 per kilowatt hour. So there you would have a business case for synthetic fuel, but I don't think here close to Montreal, or it's far down the road.
Thank you. We have actually more questions, especially one on EV charge from combined cycle gas, but unfortunately we don't have time. What I would like to do is first ask each of our panelists to present their concluding remarks in 1 minute, and then ask you audience to actually answer to a poll that we have been asked in terms of engineering month to kind of answer. So with that, I would maybe Peter, please present your concluding remarks.
Well, first of all, thank you very much, Soheil, and Anne-Marie and Robert and the other organizers, and thank you so much to Christian. Super talk, learned a lot from it, and I hope we can be in touch in the future. The future automobile is coming. Everybody's working on it very, very hard. You see the headlines. There's a lot more going on that you don't see. But again, it has to be based on a business case. It has to make sense financially, and it has to be something that people will buy that complies with the regulatory requirements of the various governments. I think it's vital that Canadian governments harmonize their regulations with legislation elsewhere. The Canadian market is not big enough to sustain unique Canadian products. That I sincerely believe that. And if we try to do that, we will just simply hurt affordability for Canadians of new technology. And overall, that will mean people will keep on driving old cars, which are not as safe and which pollute more. So there's lots of opportunity going forward. excuse me, don't let anybody tell you that the whole future is software and electrical stuff. It is a lot of that, but everything that we're doing today will continue to be important, and it will all need strong engineering and the best engineers to maintain Canada's place in that sector. Thank you.
Thank you very much, Peter. But Christian, please proceed.
I would simply refer to a TED talk that I watched recently, listening to John Kerry, and he was, let's say, comparing the goal of, let's say, reaching a net zero economy by 2050 to when in the 60s, beginning of the 60s, the American wanted to go to the moon. And he says that's the same kind of challenge we're facing, and innovation will be key. And so, and that's I think where we need to look at. I mean, innovation will be key to succeed to reach that 2050, let's say, goal of net zero economy.
Really appreciate that. Thank you very much. Thank you both. I mean, you guys did an outstanding job. I really appreciate it. It was extremely informative. It was questions were good, and you did a great job on questions as well. So many thanks. I think actually on your note, I would say the kind of getting to net zero by 2050 would be maybe 10 times more even difficult than, you know, the moonshot, etc. So on that note, I think maybe if we can have that kind of poll, etc., so we can respond to that, that would be great. Thank you very much. It was a great response, and we appreciate that. By the way, I just not only want to again thank our distinguished presenters, but also all of you for your active participation and the great questions that you posed, and hoping that we are going to meet again soon and look at another aspect of net zero by 2050. Thank you very much. We close this session now. Thanks.
Thank you.
Thank you. Bye, everyone.
Bye.
Bye.